also show some interesting in about. Today we are again welcome Professor Pierre Ruiz-Martinez and Shegwin for their kind coming in, and so the agent will present some thoughts about the catalysis. According to the program, today will Pierre Ruiz-Martinez will be a young promising scientist. He got his PhD from Spain, then moved to work in Utrecht University with under the group with Professor Philip Martin. And today he will present a talk already got an award before in the International Congress of Professors this year ago. So he got the award of the Young Scientist in the International Congress of Professors 2004 with attendance of more than 2,000 audience during such lecture.
Just like here.
Yeah? Like here.
It was the International Congress of Professors held every 4 years, and join all the capacity members worldwide. So you could imagine all the editors, all the societies, and all the heads, big heads in this field attending such talks. It's very good celebration for the persons interested in this technology. So the title of our talk today is Imaging Micro-Spectroscopy Methodologies for studying individual cracking catalyst particles throughout different life stages. Thank you very much, Mohammed. First, good morning, everybody, and I would like to thank all of you for inviting us to your country and to your university. I think I talk to you for all of us that we are really nice to be here, and we appreciate a lot your kindness and everything. I want also to apologize for my voice because I lost it during my flight to Saudi Arabia, so maybe I'm not 100% recovered yet, so please my apologies about it. And although I'm working in Utrecht University with Professor Berthehausen, I'm not from the Netherlands. I'm coming from Spain, more specifically from Granada, the south of Spain, which was the last Muslim kingdom in Spain. And I'm showing you here a few pictures of my home city, where you can see, for instance, the Alhambra there. It's a nice Muslim palace in my city. It's also surrounded by different gardens and fountains, and it resembles a lot how is the architecture here in Saudi Arabia. And I feel also that it's very close to my country, also the soil here and everything, so it's nice to see how close my culture is related to yours. And for instance, this was a village built by the Muslims in that era, and that is where for instance, my father born and grew up. But coming back to my topic, so today I will talk about a specific catalytic system. So yesterday, Berthehausen was highlighting all the different lines in our research, in our group. Today I will talk about a specific catalytic system, which is fluid catalytic cracking catalyst particles. And I will show you how to study this system at the single particle level with two different approaches. One consisting on confocal fluorescence microscopy, and the second based on an X-ray microscopy methodology. And as I mentioned before, fluid catalytic cracking is a very important catalytic system in oil refineries, and basically consists in the conversion of heavy oil fractions into more valuable products, such as gasoline or olefins. So you can imagine the importance of this system, and approximately like 30% of the gasoline of the cars which are consumed by our cars are coming from this catalytic unit. So it highlights how important it is. So here you can see a skin of an FCC unit, and basically the catalyst is coming in contact with the oil feedstock here in the riser, where the reaction takes place to then go to the stripper, where the hydrocarbons are dissolved, and subsequently the catalyst is going to this unit called regenerator, where the code generated during the cracking reaction is burned off to finally come back again, regenerate it to the reactor, and then start a new catalytic system. But if we focus now on the catalyst, here I'm showing you an SEM image of a single FCC catalyst particle. And they are spheres of an average of 70 microns, and to give you an idea, what is 70 microns is more or less the thickness of a human hair. So it's quite small. And these small particles contains a mixture of first zeolite, which is the active phase in this material, which can be zeolite white, which is the one in charge of converting the crude oil into gasoline, or ZSM5 if you want to boost the formation of light olefins, for instance. And this zeolite is embedded into a matrix of alumina, silica, and clay. So you can imagine in such a complex system of mixture of components, there's such knowledge about what exactly is each component, and also what is the activity of the material, is still unresolved so far, or not well understood. But also it's important to know how this catalyst deactivates, because it's not also known how it deactivates at the single particle level. And that's the motivation of this work. And I will show you today two different methodologies. The first one to gain insight, to study the activity and the acidity of this catalytic material at the single particle level and throughout different life stages. And when I say life stages, I mean different degrees of deactivation. And in the second part of my talk, I will talk about another approach based on X-ray microscopy, and I will show you where the poison, very important poisons in this system, nickel and vanadium, are deposited on this system, and also what is the effect of those poisons in the active phase of the material, which is the zeolite. So if we go first to the first part of my talk, I divided also in three parts. One based on a reaction probe, the thiophene oligomerization, then styrene oligomerization, and finally I will talk about a new novel approach integrating electron microscopy and fluorescent microscopy, a new approach used for the first time in the field of catalysis. So if we start with the first of the topic, this research was inspired in biology, and in biology the people use confocal fluorescent microscopy in combination with different dyes in order to resolve the structure of cells and tissues. And then with this approach you can nicely visualize different events in these cells and tissues, as you can observe in these figures. And that was one very important in the field of biology. And what we want to do now is translate that knowledge to the field of catalysis. So that's what we try to do. And the first approach was done in 2006 and published in Nature with an LDH material. And in our group, we use this technique in order to visualize the activity of single particles, single ideal particles, for instance, ZSM5 and sample 34 material, but also as highlighted Bertheusen yesterday, to unravel the integral structure of these materials. But now we went one step more, and we wanted to study a real catalytic system, as I mentioned. So when it's confocal fluorescent microscopy, basically it's the combination of a microscope and a laser, coupled to a laser, and then this laser is focused on your sample, and then your sample fluoresces, and this photomultiplier on the top is collecting that light and making these very nice images, as you can see here. But another very important part of this system is the pinhole there on the top, because enable always to get into the detector light coming from a single plane of our material. So if you want to make a 3D reconstruction of your material, you have to just scan it from the top up to the bottom. So if we take this confocal fluorescent microscopy approach, and we want to visualize the activity of our material, we have to use a probe molecule. In this case, we use the oligomerization of thiophene, and it basically consists in that the thiophene reacts with the roasted acidity of the material being protonated, and then subsequently reacting with other thiophene molecules, forming these oligomer carbocations. And this is very important because this oligomer carbocation has optical properties, so they are able to absorb light and also emit fluorescence, and they will be attached to the roasted acidity. So they will report us what is exactly the activity of our material. So if we take our confocal fluorescent microscope and we do this probe reaction under the microscope, we generate these very nice fluorescent images where the bright red spots are locating the roasted and the zeolite in a single particle. As you can see here, we can also measure the size of these zeolitic domains, which are around 2.5 microns, which is in line with the zeolite that the producer are introducing in the material. But we went a little bit further, and we wanted to study also, because this is a fresh material, we also wanted to study how is the fluorescence in a deactivated sample. So what we did is we did the same approach in different deactivated samples, and we observed that the fluorescence was fading away with the deactivation of the catalyst. So, depending on the severity of the deactivation, mild, medium, or severe, the fluorescence was fading away. So we make a belief that there was a correlation between the fluorescent intensity and the activity of our material. But this is all based in one single particle. So in order to put more a thorough study, we make statistics. So we study different individual particles and different domains within the individual particles, and we try to average all that information and give more consistent data to our analysis. So that's what we did, and we observed on the right side that the intensity was following that trend from fresh to mild, medium, severe, which nicely corresponds to the activity of the catalyst in a real cracking gas soil process, so which is going from fresh, mild, medium, and severe. So it seems that there is a nice correlation of the activity and the fluorescence intensity, but with an added value, which is that we can selectively localize what is the activity of the material at the single particle level. But in that case, they were ideal systems. They were system deactivated in the lab. So what we want to do now is to study a real catalyst deactivated in a real FCC unit, which is called equilibrium catalyst. And we wanted to see if we were able to predict the activity of this material. So if we take this equilibrium catalyst in the conversion of the vacuum gas soil, we observe that the activity is lying in between the medium and the severe deactivated catalyst. So if we do now our staining approach, we observe that in that case it's also lying in between the medium and severe deactivated sample. But of course, I mean, this is also bulk information, so we can also extract more information out of it. And what we did is to study how is the average activity of single individual catalyst particles. And here you can see that activity, and you can observe, for instance, that the activity of an equilibrium catalyst, which consists in a catalyst with particles with different lives, has a broader fluorescent intensity as compared to the ideal deactivated catalyst, the medium and severe, which have more or less the same activity. So this is showing how inhomogeneous is a real catalytic system. So that was with the thiophene oligomerization, but we can also do the same with other proof reactions. For instance, styrene oligomerization. And the styrene oligomerization is following a similar reaction pathway. So the proton is protonated in a bronze acid site, and then it's reacting with another styrene molecule, leading to the formation of these fluorescent molecules, which is the same. I mean, they will be attached to the bronze acidity, so we will be able to visualize the activity of the material. But in this case, for instance, we can also distinguish between if it's in Z5 material or in a white zeolite, because the oligomers are completely different if it's a white zeolite or Z5. So we can make the same approach, same catalyst, we observe similar patterns. So very bright fluorescent domains, which correspond to the zeolitic domains in the catalyst. So far, since that this is also working as tyrosine oligomerization, we also did the same approach with a catalyst containing Z5 and zeolite white. We were able to visualize the activity of the material and to confirm that this activity is coming from the zeolite. We did the same in a particle which doesn't contain a zeolite, and as you can see, there is no fluorescent in it. So the activity is coming from the zeolitic domains. We did the same approach. So fresh, deactivated, the fluorescence was fading away, so it seems that can be also done with this staining approach. But so far, I mean, the results were the same. But what else can we add with this proof reaction? With this proof, what we can do is, for instance, just use different substituents, and then they will have different reactivities with the bronze acidity, so then we can titrate different strength in the acidity. So that's what we did. So we tested with 4-methoxystyrene and 4-fluorostyrene. Methoxystyrene is reacts very easily, so it will titrate strong and weak acid sites. But on the other hand, fluorostyrene needs more strong acid sites, so we will only visualize the strongest acidity in the material. So as you can see here, in a FCC catalyst with the zeolite white, you observe that the fluorescence in methoxy is much higher as compared to fluoro, which means that you have a distribution of acidity strength in this material. So we can also visualize how different is the acidity in this material. If we make the same methodology to a FCC catalyst containing Z5, we observe that in this case, in Z5 material, the acidity is more homogeneous. So they have the same type of acidity. So that's the added value of this proof reaction. So I show you that we can visualize the activity of this material at the single particle level, but this fluorescent, confocal fluorescent microscopy has some limitations. For instance, is the spatial resolution. So we are limited by the diffraction of the light. So the light, it has some limitations, and it's giving us the resolution of our technique, which is around 0.5 micron, 1 micron. But if we want to overcome this diffraction limit, we have to do other approaches. For instance, what we did is integrate confocal fluorescent microscopy with electron microscopy. So with confocal fluorescent microscopy, we will be able to visualize the activity of our material, and with electron microscopy, we can give more details about the structure of these fluorescent domains with a higher resolution, which can go up to even sub-nanometer resolution. So that's what I said. I mean, this island approach is basically the combination of a confocal fluorescent microscope and an electron microscope. And I will show you here a sketch of how this combining approach works. So basically, you attach a confocal head into a electron transmission microscope, you generate the fluorescent images of your material. Then you can put it back your confocal head, tilt your sample 90 degrees, and then collect your electron microscopy information. So then you will have, at the same time, and in the same spot, the fluorescent information plus the electron microscopy information. So that's what we did. And this is the experimental approach. So basically, we took our FCC catalyst particles, embedded into a resin, cut it into very thin slides of around 80 nanometers, because in this case we need very thin slides because the electrons have to go through our sample. Then we place it in a TEM grid and then make the combining approach. So we did it for our FCC catalyst particles, and here you can see a TM image of a slide of an FCC catalyst particle containing zeolite white, and here you can see the combination of the electron microscopy and fluorescent microscopy. So you can see that you have like very bright spots, but also places where you don't have fluorescence. So we can define different regions in our material. But if we take a look into how is the structure of those places, it's completely different. And I will show you more clearer now in a magnification. So you can see that the bright fluorescent images, they are more electron dense and angular. On the other hand, the non-fluorescent images are more, they have more non-crystalline material, and also some platelets, as you can see, which are coming from the clay. So it makes us believe that. So we wanted to study more into detail this. So we sort out the different structure into two different types. So the type 1, which are those electron dense material, and the type 2, which are those mixture of amorphous system and platelets. We observed that this type 1 has a higher fluorescent intensity as compared to the type 2, and then we have also other regions in the material, which is a mixture, a combination of type 1 and type 2. And those have like an average intensity as compared to the 1 and 2. So makes us believe that the type 1 is the zeolite domain in our material, which also verified by measuring just only the zeolite by electron microscopy. We also make electron diffraction, and we verified that what we were observing is the zeolitic domains in the material. But we can also extrapolate this. That was for a fresh catalyst particle. We can also extrapolate it for a deactivated sample. And what we did here is we take a fresh sample, steam it, via steaming, we are basically removing the aluminum from the zeolite and make it less active. So that's what we did. As you can see, the fluorescence is less intense as compared to the fresh material. But if we take a closer look into the less fluorescent material, they look like zeolite, but it seems to be like a more like with a amorphous material on the top, which is the gamma alumina after dealumination. So with this, we can draw some conclusions from this part, and I hope I have shown you that with fluorescent microscopy we can visualize the activity of our material, not also at the single particle level, but with different particles, so inter and intraparticle levels. We also observe that there is a link between the activity of our material and the fluorescence of our confocal fluorescent images. And also, I show you that with the iron approach, we can take a look into more detail with higher resolution about how is the structure of this material. So that was related to the activity of the material. Now I will focus in the deactivation of the system. And as I showed you before, I mean, in this catalytic system, in this catalytic cycle, the catalyst is little by little being deactivated. And this deactivation is mainly coming from the metals coming from the oil feedstock, basically nickel and vanadium. So this nickel and vanadium are depositing on the catalyst and promoting dehydrogenation reactions. These dehydrogenation reactions actually are forming more coke in the catalyst and then blocking the active site and all the porosity of the material. In the case of nickel, it's very active in dehydrogenation. In the case of vanadium, it's also a dehydrogenation catalyst, but it's also destroy the zeolitic domains, the material. So what we did now? So for those study, we did an X-ray microscopy study. So we have to go to a synchrotron facility. So that's what we did. We went to Diamond in close to London, and we used the beamline IV16 with an X-ray energy of 10 kiloelectron volts and spatial resolution of 5 by 5. And here you have a cartoon about the experimental approach, which is basically we have the X-rays coming here. They are focused by a sound plane into our sample, and then we can collect the X-ray fluorescence in this collector, and also XRD information with the CCD camera. So at the same time, we can collect X-ray fluorescence, which is elementally sensitive, and we can also collect the XRD pattern of the material. So we study a fresh and deactivated sample, and here I'm showing you some X-ray fluorescent images of a fresh catalyst sample. And as you can see, there is no signal coming from nickel and vanadium. But if we study a deactivated sample, we observe, for instance, that the nickel has a very pronounced axial distribution, which means that it's being deposited on the external surface of our material. In the case of vanadium, it's also an axial distribution, but it seems to be more mobile. So it's depositing on the surface of our material, but also diffusing inwards. So that's the information that we can extract from these XRF maps, but we can also make same spectra coming out of this. So we can collect X-ray information, X-ray spectroscopy coming from this bin line. So we can study the oxidation state of this material, but also the coordination, the surrounding of those metals. And that's what we did, and we observed that, for instance, the nickel is in the 2+ oxidation state and octahedral. In the case of vanadium, we observed that the vanadium is located in our catalyst in 4+ and 5+ oxidation states in a octahedral environment. So we can study the location of our metals, but also the chemistry in the metals. But now the next question is, how is those metals affecting the active site of the materials, so the zeolite itself? With the previous approach, we can study how is the deactivation of the zeolite. So that's what we use XRD tomography in order to see how is the crystallinity of our material changing with the deactivation. So here I can show you an example of XRD pattern of a fresh and equilibrium catalyst, and we were able to visualize, to observe the different crystalline phases of our material, zeolite white, clay, anatase, and boehmite, but also the transformations that they suffer after the activation. For instance, the clay is going through another phase called mullite, the boehmite is going to another phase called gamma luminance. So that's bulk information. But we can also make a reconstruction of those measurements and make a 2D image where we can visualize the different components of the material. And that's what we did for the fresh and equilibrium catalyst. For the matrix components, as you can see, clay, boehmite. And we can observe, for instance, that in some cases we have a lot of heterogeneities. For example, in the clay, we have very hot spots in some of the particles. But that's regarding the matrix component of the material. But if we take a more into detail look into the zeolite domains, the active phase in the material, we observe that in the case of the fresh sample, the zeolite is unhomogeneously distributed on the catalyst. But when it's deactivated, we observe that the deactivation is more severe on the external surface of the material, so at the periphery, where the metals were located. So this is telling us that there is a relation between where the metals are deposited and the deactivation of the zeolitic domains. But we wanted to extract even more information out of these XRD patterns, and we take a closer look into the 111 peak of the zeolite Y. And we observed that after deactivation, this peak was shifting. And this shift is due to, well, most likely is due to dealumination of our zeolite. So by dealumination, we make the unit cell of the material smaller and then shift. So we can also visualize the dealumination of our material at the single particle level. So that's what we did. And we observed that in the case of the fresh sample, the silicon to aluminum ratio of our material was very homogeneous, but in the case of the deactivated sample, we observed a higher silicon to aluminum ratio on the external surface of the material, which means that the severity of the deactivation is higher at the periphery, where the metals are located. So in this, there is a relation between the deactivation and the position of metals. So we can envisage a deactivation mechanism and try to understand what's going on in the system. So here, I show you, like, this is a representation of the fresh catalyst where the red spots are the zeolitic domains. So during the catalytic test, metals are deposited at the periphery of the material, and then when they start being more deactivated, they are forming coke, and then this burn-off of the coke in the regenerator are creating like a very hot spot on the surface of the material, and then severely deactivating the periphery of our material and remaining more stable the inner part of the system. So that's one envisaged deactivation mechanism, but it can also be due to, for instance, the deposition of vanadium, which is believed to basically dissolve the zeolites and then destroy them. So these are the two main mechanisms that we believe are going on in the deactivation of a single catalyst particle. Summarizing, I'm showing you that the deactivation of the material seems to be more located on the external surface of the material, so the metals are deposited at the periphery. I also show you that with absorption spectroscopy, we can also study the oxidation state, the chemistry of these metals. And it seems to be that the zeolitic, the zeolite, we can also visualize it by XRD microscopy, and seems to be related to the deposition of the metals. So finally, I would like to thank some people. Of course, Bert Behausen, supervising the research, Inge Burmans, who was involved in the first part of my talk, Malte Kareman, who was involved in the island approach, Andy Bill and Upa Kuldeka for helping me in the X-ray experiments. The people from Diamond Light Source, especially Paul Quinn and Fred Mosselman for the X-ray experiments. Also Alve Marle for providing the catalyst, and also very nice discussions, especially Elko, Jap, David and Williams. And of course, the financial support that I have in my first 2 years in Utrecht University, coming from ASPER. And I would finally like to thank you, all of you, for your kind attention. Thank you.
Thank you for your nice and impressive talk as well. And it's open now for discussion. Any questions?
like my specialization is not catalysis, so you can excuse my ignorance for that. What I understood from the beginning is that you prepare the catalyst, but what I understood at the end is you receive it from somewhere else, right?
Yeah, it's a commercial catalyst.
Commercial catalyst. So like I was thinking about how the reproducibility of the catalyst itself and how they make the recipe to have 4 components, as you say, zeolite, alumina, clay, and what was the fourth one?
Alumina, silicon, clay, and zeolite.
Okay. Like, I would like to know what is the role of each one. I see the active component is the zeolite, right? Why we need the other 3?
Yeah, the other thing are basically because you need in your particles you need, for instance, strength, because it's a fluidized bed, so that the particles are like hitting each other. So you need some mechanical strength in your material, but you also need porosity, and this porosity is also coming from this matrix component. Additionally, they also add other additives to this matrix in order to decrease, for instance, the severity of the deactivation, things like that.
Yeah. And you mentioned at the end, like the vanadium reacts or poison the zeolite. Is there any proposed reaction about that, or just like cover the surface?
Yeah, there
to
are.
prevent the active site itself from the reaction.
Yeah, there are a few mechanisms proposed, and basically it's in the regenerator. So you generate a lot of heat, right? And it's an oxidant ambient, so you create vanadium 5+. But you have also water. When you have vanadium 5+ and water, you can form vanadic acid. And this vanadic acid basically can dissolve your material. So that's one of the proposed mechanisms. The second is you can also take this vanadium and introduce it into the framework of the material. But we haven't seen that behavior, because in the same spectra we didn't observe vanadium in the tetrahedral coordination, which means, well, make us believe that it's not introduced into the framework of the material.
Although the picture saying that amine has in the surface and then goes to the bottom. According to the unit radii of vanadium relating to nickel, more possible to dissolve vanadium in the structure of the material. So there is also solution of in the crystal lattice other.
Yes, exactly.
And this is why also there is a change in the lattice parameters and the.
Yeah, that's where you have also more mobility. So you're creating the acid, and it's like basically going inwards.
So the thing is not the eggshell like the nickel.
Yeah,
like
nickel is less mobile,
yeah.
so it stays just on the surface.
One last question.
Yeah.
Is there any more results from other catalysts rather than that one you received, which you showed us, 70 micrometers? Just one catalyst, right?
Yes.
Just one catalyst. Did you try to more catalysts?
Yeah, we tried different batches, but in the X-ray approach, due to the limitation of time, because we don't have a lot of time in the meantime, we also studied one single batch of catalysts. But in the confocal present approach, we studied different batches containing with same formulations but with different providers, for instance, with different additives, with sets and 5, and all of them works.
I would like just to have a small comment regarding this issue. For the controller measurement, it's possible because it's in the lab. For the beam time means you have to reserve the beam for 2 days. And sometimes you go there, sitting, and beam is off. So you have to reserve again for after 1 month, 2 months, in order to carry single experiment. So those people are working day and night for a few days and other to
24/7
to bring science the reality. This is really a very thankful work and so please, another question.
Yeah, I'm interested in the thiophene oligomer and styrene oligomer. Is it only a dimer, trimer, tetramer, or
Yes.
a long chain? Especially in the thiophene, is there a conjugation between the two?
Yes.
And if it is so, can we go to conducting, so you can make some interesting long chain polymer where we can conduct electricity.
Yeah, you're right. You're right. So with this approach, I mean, you can make the polymerization. You can also create polymers. The problem is these polymers are not visible with our approach. So we are basically measuring the intermediates of that polymerization, let's say. But the good thing is that these intermediates are always located where the active site is, because there's a charge balance.
Yeah.
So we have the protonation and the protonation. So I'm sure we are creating polymers, but the active sites are located with these oligomers, like dimer primers. And regarding the chemistry also of these small oligomers, we have observed other different types of polymers. So like more conjugated ones. So if you see the UVB spectra, you observe also oligomers with 3, maybe 4 units.
Yeah. It's interesting.
Did you ever consider a simple Hammett indicator? I know it's a very well-known reaction to determine differentiation between the peroxide and crystallite. It's well known. But in previous days, people used to use Hammett indicators.
Yeah.
But you can simply see with your own eye change of the color, which have fluorescent properties. And maybe just did you ever consider using Hammett indicators rather than complex reaction?
Yes. So we are also working on that. On the thing is, this Hammett indicator. I mean, so we have the zeolite, right? And the zeolite has this a micropore system. So in this case, in white zeolite, we have a pore entrance of 0.7 nanometers. In the case of certain fine, we have 0.55 approximately. These Hammett indicators, they are large organic molecules. So it's very difficult to go inside the structure of the zeolite unless you make like a synthesis of those Hammett indicators inside the zeolite. But also for your information, we are able to selectively stain the other part of the material, I mean the matrix, because it has larger pores, so we can introduce different indicators there and see how the distribution of that phase. I mean, Bert was showing yesterday this Nile blue, which is an indicator.
Okay. Any other questions? Because here I have just because I have an interest in the clay. I mean the anemic clays on the outside. So it is special indicators of molecules, but also used to test for the basic sites of such image. Because you present something at the beginning.
Yes.
And I would like, I myself believe that such material is not 100% safe. It could be bifunctional. I mean, there is some acidic sites, etc. So could we think for the product to quantify or to differentiate or to prove the right or false this speculation?
I would say it's possible, yeah. But you need crystal materials with sufficiently big to be measured with our approach. So the resolution of our approach is 0.5 micron, so you need large crystal in order to resolve where is located this basic site and acid site. So if you have those large crystals, I believe that it's possible to visualize where are the basic and the acid sites.
This would be nice. Okay. Okay, so at the end of this talk, I would like to thank Ruiz-Martinez for this nice presentation today, as well as I would like to thank Professor Frederick Halden, Shengwen for their coming to University of King Abdulaziz University. You are more than welcome at any time, and for kind collaboration in the research. We as a group here in the TU are pleased to invite you at any time to continue such kind of scientific discussions. Thank you very much for the